Hey everybody, Trey here. Welcome back to another episode in this Skew-T and Hodograph series. We're coming toward the end of the series here. We're going to finish up looking at the bottom portion of the sounding in this video, and then we're going to do our last video next time, and that is going to be kind of putting everything together, doing some application type stuff with soundings, trying to look at how forecasts are made with soundings. We're going to do some real-world applications there to kind of put everything together that we've talked about in this series. But for now, we're going to finish out looking at the bottom portion of the sounding. So if you recall, in our last video, we talked about this box down in here. The last couple videos, we talked about all the parameters down here in that bottom left box there of the SPC and model soundings. And today we're going to finish out that bottom portion. We're going to take a look at these three boxes here, and we're going to tell you everything that is part of these three different boxes on the bottom portion of the sounding. So without further ado, let's go ahead and get started, and we'll take a look first at the kind of middle box right in here. And whereas last couple videos, we talked about this box here, which was our thermodynamic parameters, these are going to be our kinematic parameters, or basically our parameters derived from the winds in the atmosphere. So, as you can see here, we've got several different layers listed here. We've got surface to 1, surface to 3, effective inflow layer, so on and so forth. These are going to be our layers here, listed kind of on the left-hand side of this box. And on the top, we have 4 different parameters that are going to be calculated for each of these different layers. And so we'll kind of draw a line here as we're going to start with this top portion of this middle box here. So these 4 parameters here listed on the top side of the box. This is going to be our storm relative velocity, SRH. And if you recall, storm relative velocity is basically the area that's swept out between the hodograph and the storm motion vector, particularly the bunker's right mover storm motion vector. So we can calculate the storm relative velocity for each of these different layers, 0 to 1, 0 to 3, effective inflow layer, and so and those are going to be the 3 layers that the SRH is calculated for. You can see down here that the SRH is not calculated for these remaining layers. But each of these different layers has a purpose when we're talking about storm relative velocity. Next, we have our shear, our wind shear. Basically, as we've talked about many times in this series, that is going to be our change in wind speed and direction with height. We can actually calculate a value from that pretty easily from the hodograph. So, for example, if we're looking from 0 to 1, bulk shear, surface to 1 kilometer bulk shear, we would just draw our vector from the surface to 1 kilometers here on the hodograph, and we would calculate the length of that vector. We'll do that here in a second. Now we have our mean wind, and the mean wind is basically exactly what it sounds like. It's a pressure-weighted average wind in a layer. So you basically add up all the winds, their direction and speed, and you take an average of that, weighted by pressure, some mathematical formula that's used to kind of weight based on pressure within a layer, but basically you can think of it as the average wind in a layer. Then finally we have the storm relative wind, which is pretty much the exact same as mean wind, but we're subtracting out storm motion. Anytime you hear the word storm relative, we're subtracting out that storm motion, and particularly we're looking at the bunker's right mover storm motion. So we're basically taking our mean wind in a given layer, and we are subtracting the storm motion, the right mover storm motion, from that mean wind. So it's basically what the storm is feeling in a certain layer. And as far as what's useful and what's not, we'll definitely talk about storm relative velocity and bulk shear here within these certain layers. Those are going to be your most important quantities, as they're going to discriminate between tornadic and non-tornadic supercells, supercell and non-supercell thunderstorms. So these are going to be your most important parameters here when we're talking about kinematics. It's going to be your storm relative velocity and your shear. The mean wind and the storm relative wind are not super widely used in severe weather forecasting. The mean wind is, especially the storm relative mean wind, it's going to help you basically infer the precipitation distribution within supercell thunderstorms. When we're given an actual sort of value, it's not super useful. You can tell, given the strength of the storm relative wind in a layer, how much the precipitation in that layer will be vented, for example. And so it can be useful when you're making a forecast on the structure of a supercell, what the supercells might look like, high precipitation, low precipitation, how well the precipitation is vented off in a certain layer. But overall, when we're just trying to forecast supercells themselves and tornadoes themselves, it's not overly important, but it can be important when forecasting supercell structure. So I don't use mean wind and storm relative wind that often. I mainly look at the storm relative helicity and bulk shear. But let's get started here. Let's take a look at each of these layers. So this first layer listed here is going to be our 0 to 1 kilometer layer, our surface to 1 kilometer layer. And you can see here we've got values calculated for that: storm relative helicity, shear, mean wind, storm relative wind. And the 0 to 1 kilometer layer is a very good discriminator, particularly when we're talking about storm relative helicity in tornadic versus non-tornadic supercells. And there's been quite a bit of research that has been done on this. Thompson et al. 2003, Rasmussen and Blanchard 1998, Thompson et al. 2007, and so on and so forth. But it's been found that the 0 to 1 kilometer layer is a good discriminator of tornadic versus non-tornadic supercells. So you have a supercell in this example environment we have here in the background. You can see the storm relative helicity is above 350 meters squared per second squared. That's extremely high. So basically we're calculating that area between the right mover storm motion vector and the that 0 to 1 kilometer layer. We're taking that area under the hodograph between that storm motion vector and the hodograph. And that has come out, in this case, to 361 meters squared per second squared. That's an extremely high value. Again, when we're talking about 0 to 1 kilometer storm relative helicity, we like to see values above about 150 meters squared per second squared. As far as a kind of rule of thumb discriminator value for tornadic versus non-tornadic supercells. And 361 is very, very high. So in this environment, we're seeing very high 0 to 1 SRH. We're also seeing very high 0 to 3 kilometer SRH. And this 0 to 3 kilometer layer is not going to be as important as your 0 to 1 kilometer layer. For years, it has been used to estimate the inflow layer of a thunderstorm in this given environment. We've talked about previously in this series, and we'll talk about more in a second, the effective inflow layer here, which is a much better sort of estimate of the inflow layer. But the 0 to 3 kilometer layer was basically a fixed layer that was used to estimate the inflow layer of a thunderstorm. So basically the air that was important to the thunderstorm, the air that the thunderstorm was feeding off of, was estimated using this 0 to 3 kilometer layer. It's been found again that the effective inflow layer is a lot better estimate of this inflow layer, and that the 0 to 1 kilometer SRH, shear, etc., is a lot more of a discriminator between tornadic and non-tornadic thunderstorms. But nonetheless, storm relative helicity, shear, and these other parameters are calculated for the 0 to 3 kilometer layer. Not super important. I do look at it a lot, the 0 to 3 kilometer SRH in particular, just as kind of as I'm looking at the overall environment, it's a nice number to kind of estimate the overall spin in that 0 to 3 kilometer layer. But again, I like to focus on that 0 to 1 kilometer layer for discriminating between tornadic and non-tornadic environments. Now, the effective inflow layer. Again, we've talked about this previously in the series, but the effective inflow layer is going to be that layer in which CAPE is greater than 100 joules per kilogram, and SIN is going to be greater than negative 250 joules per kilogram, or you can think of it as less than 250 joules per kilogram of SIN. Of course, we have that negative there, so we're going to say greater than negative 250 joules per kilogram. That's going to be your effective inflow layer. And you can see that it is plotted on the hodograph as these blue lines between that storm motion vector and wherever those parcels that are lifted from that sounding meet these two criteria. And so the area underneath that curve is going to be the effective inflow layer, storm relative helicity. And this is going to be a lot better of a estimate for your inflow layer than that 0 to 3 kilometer layer, because it is going to change for different environments. That 0 to 3 kilometer layer may be too shallow, it may be too deep based on the actual distribution of instability and SIN in that lowest 3 kilometers of the atmosphere. So this 0 to 3 kilometer layer is often not going to be a great accurate estimate of that inflow layer. You can see here in this example, the inflow layer extends up to only about 2 kilometers, whereas if we would calculate that 0 to 3 kilometer SRH, we would have had to go a little bit higher, whereas the air in this region of the atmosphere, that 2 to 3 kilometer layer, does not meet both of these criteria. So that effective inflow layer is going to be a lot better, and this is the value I really like to hone in on, that effective inflow layer SRH. It's a really good discriminator between tornadic and non-tornadic supercells because you're taking into account all of the air that the thunderstorm is going to eat, especially that low-level air that the thunderstorm is going to eat, so to speak. And if you have a lot of spin in that effective inflow layer, no matter how deep it is, of course, we'd like to see it a little bit deeper rather than a shallow effective inflow layer. When you have a deep effective inflow layer with a lot of storm relative helicity, more often than not, you're going to see an environment that is very conducive to tornadic supercells. You can see here in this example, 401 effective inflow layer SRH here. Very, very high value. Again, we like to see values above about 150 meters squared per second squared of SRH. Effective inflow layer SRH here of over 400 meters squared per second squared. So I like to use the effective inflow layer SRH. It's one of the values I hone in on when I'm looking at this portion of the sounding. So very important is that effective inflow layer SRH. Then we move on to our deep layer parameters. These are going to be our deep layer parameters here. You can see the first layer that is listed here is the 0 to 6 kilometer layer. Then we have below that the 0 to 8 kilometer layer. These are going to be your sort of deep layer shear parameters, because we're looking through a much deeper layer of the atmosphere, of the potential storm that may go up in this atmosphere. 0 to 6 kilometer, the 0 to 6 kilometer layer, you can see again that the SRH is not calculated for these layers because it's not super important in a deep sense. We like to hone in on those low levels when we're talking about storm relative helicity. But the deep layer wind shear is important when we're talking about discriminating between supercell and non-supercell environments. So when we see the 0 to 6 kilometer shear, generally above about 25 knots or so. We like to see the higher the shear, the better chance there is for rotating storms, the more that wind is changing in both speed and direction with height. And when we see a 0 to 6 kilometer shear value of above 25, usually 25 to 40 knots is kind of that transition zone for non-supercell to supercell thunderstorms. When we see anything above kind of this threshold value, supercells are much more likely. And you can see in this case we have very strong shear, 0 to 6 kilometer shear of 80 knots. That's extremely high. And again, this is easy to figure out from the hodograph itself. So all we're doing is we're drawing a vector from the bottom of our layer to the top of the layer. So in this case, it'd be the 0 to 6 kilometer layer. So we're basically drawing a vector from the surface up to 6 kilometers. And you can calculate that. You see 80 knots here. You can see it's basically almost at the origin, a little bit to the right of the origin here, but it goes up. This ring here is 80 knots, so we're a little bit more than 80 knots. You can see we're a little bit more than 0 here, so we're at about 80 knots here. 0 to 8 kilometer shear extends a little bit farther. You can see it is at 87. A little bit covered there, but it is 87 knots of 0 to 8 kilometer shear. Very, very strong shear in this layer. The 0 to 8 kilometer shear is not super important. I never really use it when I'm making a forecast, but the 0 to 6 kilometer shear is important. I like to use that as a discriminating factor, particularly in those events where the shear is kind of on the margins for supercells. So, if we have a nicely unstable environment, nice moist environment, if we're talking about shear that is kind of on the margins, I definitely like to see that 0 to 6 kilometer shear value above about 25 to 30 knots for a better chance of supercell thunderstorms. So next we have our cloud layer, which is basically from the lifted condensation level up to your equilibrium level, because basically that's going to be the extent of your theoretical cloud that is going to develop, that theoretical thunderstorm cloud that is going to develop in a given environment. Basically, we've talked about the LCL in previous videos. That's going to be that first point where the parcels become saturated. So basically your lowest theoretical cloud base. Then we go up to the equilibrium level. It's basically where the parcel becomes cooler than the environment. So basically your thunderstorm clouds are going to extend all the way up from the LCL. You can think of this as a thunderstorm anvil here. And that's going to be your thunderstorm cloud. It's going to basically stop. Of course, we've talked about that the momentum of the updraft carries it above that equilibrium level a little bit very often. That's where you see those overshooting tops. But a good estimate of the extent of the layer of clouds, or basically the depth of the thunderstorm, is going to be from that LCL to the equilibrium level. Don't use this a whole lot. Of course, you want to see a decent amount of shear in the cloud layer. That's going to favor rotating thunderstorms as well. So now we will talk about the effective shear, effective bulk wind difference. And just like the effective inflow layer, the effective bulk wind difference doesn't take into account a fixed layer. It is going to change based on a couple of things. So the effective bulk shear is basically the changing of that wind speed and direction with height, the wind shear, in the layer between the base of the effective inflow layer, so effective inflow layer base, up to 50% of the equilibrium level. So it's very similar to the 0 to 6 kilometer shear, or the 0 to 6 kilometer layer, but again, it's going to change based on the effective inflow layer base and how high that equilibrium layer extends into the atmosphere. So in this case, the effective bulk shear would start at the surface because that is the base of the effective inflow layer, and it would go up to 50%, halfway up toward the equilibrium level in a particular sounding. So it's going to be somewhere, if I just had to guess, it would be somewhere right in here. So we're basically taking the shear in this layer, base of the effective inflow layer, to 50% of the equilibrium level. And you can see that that is fairly close to that 0 to 6 kilometer layer, but again, it's going to change based on where that effective inflow layer is. So this takes into account whether or not storms are elevated or surface-based, because if an effective inflow layer began above the surface, we know that storm is going to be elevated. And so we calculate the shear in that layer knowing that that storm is elevated. Whereas in this case, for example, we know the storm is going to be surface-based because that effective inflow layer is going to start at the surface, and then we would go up 50% to the equilibrium level, which is about 6 kilometers usually, but again, it's going to change based on those parameters we talked about. So effective shear is, again, a good discriminator, a little bit better discriminator, just like the effective inflow layer. SRH is a little bit better discriminator between tornadic and non-tornadic supercells than the 0 to 1 kilometer layer, a fixed layer. The effective shear is a little bit better at discriminating supercell versus non-supercell environments than the 0 to 6 kilometer layer, which is fixed. Again, they're going to be similar very often. But again, anytime the effective shear, effective bulk wind difference is greater than 25 knots, again, 25 to 40 knots is that kind of sweet spot range for supercells, then you're going to see a greater chance for supercell development in a given environment. All right, now let's move on to the bottom portion of this middle box here. We'll start off with this first value here that is called the BRN shear, and BRN stands for bulk Richardson number. And the bulk Richardson number is basically a turbulence term in the atmosphere. There's a whole bunch of fancy math that goes along with it, but we won't get into that here. Basically, the way the BRN shear is calculated is it takes half of the difference, the vector difference between the 0 to 500 meter mean wind and the 0 to 6,000 meter mean wind. So it's basically, again, these are both pressure weighted mean wind, and we're basically taking it's basically a calculation. It tells us how likely supercell storms are in a given environment. The higher the bulk Richardson shear is, the greater chance you have for supercell thunderstorms. Never used BRN shear when I'm making a forecast. It's really not super important in the grand scheme of things, but it is there. It is a way to kind of quantify the potential for supercells in a given environment. All right, underneath the bulk Richardson number shear is the 4 to 6 kilometer storm relative wind. And as we talked about before, the storm relative wind is that mean pressure weighted wind in a given layer, in this case the 4 to 6 kilometer layer, with the storm motion subtracted out. And I don't use this much at all when making a forecast, but it is used, and it is a decent discriminator for tornadic versus non-tornadic supercells, as pioneered by Thomson 1998. Usually, 4 to 6 kilometer storm relative wind in tornadic supercells tends to be greater than 15 knots. And so you can see here in this case we have 27 knots of 4 to 6 kilometer storm relative wind, so we're well above that 15 knot threshold in this case. So tornadic supercells are, I guess, more likely in this environment than if we had a lesser 4 to 6 kilometer storm relative wind. But again, I don't use this very much at all when making a forecast, but it is there to help discriminate between tornadic and non-tornadic supercells. All right, then finally here, the bottom portion of this box, we've talked about this quite a bit. These are going to be our storm motion vectors here. And we start off here with the bunkers right and bunkers left mover storm motion vectors. Again, they're plotted on the hodograph here, our right mover and our left mover. So we've talked about this in a previous video, but again, the bunkers right storm motion comes from the fact that we have a supercell, and the early portion of its life cycle is going to develop rotation on 2 different flanks, and we get kind of 2 different storms that are going to split from that supercell. We have a left moving storm, most likely a hail producer. They tend to have very low tornado potential. Then you have a right split, a right mover storm motion that moves a little bit to the right of the mean flow. And this is going to be your supercells for the vast majority of cases that are going to be your tornado producers. It's going to be these right mover supercells. So again, the bunkers right motion and bunkers left motion are listed here both on the hodograph and down here on the in this kinematics box here. I do like to look at these when I'm making forecasts, especially the bunkers right mover storm motion, because of course, if I know that supercells are a good possibility in a given environment, I'm going to assume that the right moving supercells are going to be a good possibility. And so I like to look at this as a proxy for storm motion. In this case, pretty rapid storm motions here. 241 degrees at 51 knots. So 51 knots is pretty high, almost 60 miles an hour. When I see something like that, I like to look at the bunkers right mover storm motion as an estimate for storm motion in a given environment. Then down here we have the Corfidi vectors. These vectors right here. And we talked about this before. These are your MCS motion vectors. So the Corfidi down shear vector is an estimate of the net storm motion for a forward propagating MCS. Your Corfidi up shear vector is an estimate of the net storm motion for a back building MCS. Again, as a storm chaser, we don't like to chase MCSs all that often. We like to chase supercells. But these are here to give you a little bit of a hint of the MCS motion if an MCS is likely in a given environment. And finally, we have our 1 and 6 kilometer wind barbs that are plotted here on the bottom right of this box. Not a big discriminator for much, but it is a nice quick way to help visualize the wind shear between 1 kilometer and 6 kilometers above ground level, basically between your low and your mid levels. So the red barb is your 1 kilometer wind barb, and your blue barb is your 6 kilometer wind barb here. So as you might expect, the farther apart these two vectors are, the greater the directional shear between 1 and 6 kilometers, and you can also see the change in speed between these two levels as the actual barbs are plotted here. So you can see here the change in speed, 1, 2, 3, 4, 45 knots here at 1 kilometer, and 50, 60, 70, 80 knots here at 6 kilometers. So just a quick way to help you visualize the wind shear between the low and the mid levels. Again, it doesn't show much, but I do like to look at this just to kind of see how the distribution of shear is between these two levels. Of course, if these are right on top of each other, if these two barbs are right on top of each other, then you have likely a unidirectional wind shear profile, which is often not as good for your more isolated, discrete supercell events You can get spinning storms, rotating storms, of course, but you may not have a lot of low-level shear in that given environment. When these are farther apart, then you have a lot more directional shear in the atmosphere, and you may have a lot more low-level shear. So not super important, but I do like to give a quick glance to that when I'm making a forecast. All right, we're done with the kinematics box. Now let's move on to this box right in here. This box is going to basically tell us our analogs to our given environment. We'll start up here at this top box. This is basically the best guess precipitation type, and it basically tells you whether you're going to see rain or winter precipitation in a given environment. Of course, not super important when we're forecasting for severe storms, as it only discriminates between rain and your frozen precipitation, excluding hail. But it goes through a big old algorithm and tells you based on the surface temperature, based on the distribution of the temperature with height, whether you have warm layers aloft or not, what you might see. Obviously, in this environment, this is a severe weather sounding with a 69-degree surface temperature. We're going to see rain, most likely, as your best guess of a precipitation type. So not super important when you're making a severe weather forecast at all. Winter weather, it can be somewhat useful, but again, you can tell whether or not you're going to see rain or frozen precipitation based on the distribution by looking at the actual Skew-T itself, where you see warm noses, how deep those warm layers are, etc. So not very important at all, but it is there to give you a sort of best guess precipitation type for your winter weather scenarios. You'll notice that the best guess precipitation type feature is only available on soundings from the SPC website. You'll see on model soundings that it does not show up, only on those SPC soundings. All right, let's take a look at this box down here. This is an interesting feature you'll find on these SPC and model soundings. This is the SARS box. This SARS stands for Sounding Analog Retrieval System. And this is a pretty cool feature on these soundings. Basically, the Sounding Analog Retrieval System is a database of a bunch of historical soundings in proximity to severe hail, supercell, and tornado events. And what the SARS system tries to do is it takes the environment in a given sounding and it tries to match it with previous historical cases, previous historical environments that are, may have produced severe hail, supercells, or tornadic supercells. It's a pretty cool feature. It allows you to see some environments that may have been similar to your current environment in the past. Now, this is not a great example here. Let me move on to a model sounding here. So you can see here, for this given model sounding here, it listed a bunch of different analogs here. This left-hand split of the box here, is your supercell matches. And this right-hand box is your significant hail matches. So for the supercell matches, it has three different types. It'll have your non, which means non-tornadic. It'll have your weak, which means weakly tornadic. And it'll have your SIG, which are significant tornado producing supercells. So you can see here for this given example, it listed a bunch of different cases. Now this looks definitely like mumbo jumbo. And before I go further, you'll notice that these are color coded. Red for SIG, blue for weak, brown for non-tornadic. They're going to be color coded different for different model sites or sounding sites. You can see here on the College of DuPage site, it'll have the significant tornadic supercells in pink and the weak tornadic supercells in red, versus red and blue here on the pivotal weather sounding here. But you'll see that it's listed SIG, weak, non in all the different sounding providers. So you can see here that it's kind of a little bit of mumbo jumbo here when they list these cases. So I'll take this first one here, 99060123.mko, and then it'll have your type, which is SIG here. So this is the way that these are listed. So the first two digits are going to be the year. So this would be 1999. Then the next two digits are your month. So this would be June. And then the next 2 digits are going to be the day. So it would be the 1st of June, 1999. And then the last 2 digits here before the dot are the hour. So this would be 23Z. And then after the dot, you have MKO. This is going to be your Weather Service office or county warning area in which the sounding occurred. So I'm not exactly sure off the top of my head what MKO is, but this would be the location where the sounding was released at this given year, month, date, and time. Then, of course, you have your type of supercell. Now, on the College of DuPage soundings, you'll see they have it deciphered a little bit better for you. Let's take this top one, for example. This one is listed in day, month, year, time, office. So you can see for this top one here, it would be January 3rd of 2000 at 19Z from the office GWO, County Warning Area of GWO was a significant event. So you can see it's kind of a cool different feature to tell you to kind of discriminate different environments and try to match them with historical environments that are somewhat similar that produce significant weakly tornadic or non-tornadic supercells. Now for the significant hail, much of the same. It's listed in the same manner, but instead of the type of supercell, it gives you the size of the hail in inches here. So anything in red is going to be listed as above 2 inches. Anything in blue is going to be less than 2 inches. So pretty cool way to match significant severe hail events. You can see that it is basically listed the exact same format as the supercell matches, just with the hail size on the right side of that box. So it also give you loose matches, the amount of loose matches. So not quite these better matches here, but kind of loosely matched environments here. And it also gives you a probabilistic forecast for tornadoes and supercells. So you can see here, based on all the analogs that it took into account, the SARS analog system has estimated this sounding has a 45% tornado probability. For any supercells in this environment, 45% will produce tornadoes. And you can see here, same thing for hail. We have 240 loose matches for significant hail. And the SARS system is telling us that it thinks it has a 53%, any supercell in this environment has a 53% chance of producing significant hail, which would be over 2 inches. You can see here, though, as I said before, this is not a super accurate system. You can see here, significant tornado, 45% tornado in this environment. You can tell by this environment, high instability, very low shear. This is not going to be a tornado environment. It's going to be a very high cape, sort of low-level shear environment. Definitely a supercell environment. We can see deep layer shear at 40 knots here, but low-level shear is almost non-existent here. So you can just tell in a much more accurate fashion whether or not an environment may produce tornadic supercells or significant hail-producing supercells. Now, this is more accurate here for this environment. High cape, steep lapse rates aloft, nice deep layer shear. That significant hail may be in the cards for this setup. But as far as tornadoes go, you can just tell that these matches are just not going to happen in this environment, based on what we see with the Skew-T and the Hodograph and the other parameters here that we've talked about previously in the series. And you can see sometimes it gives you just kind of these higher end events that really just are kind of make no sense. You can see here December 16th, 2000, 18Z BMX. This was on a day in which Tuscaloosa got hit by a very strong EF4 tornado. It was broadcast live by James Spann. You can tell by this environment that that's just not going to be the case. We have very skinny cape here. It's very capped here in the low levels, some dry air aloft, and some turning in the low levels. But again, we're not really talking about a hodograph that is favorable for very significant tornadoes. Definitely some curvature in the low levels, so if we can destabilize here, tornadoes would be a possibility with this hodograph. But again, you can see very skinny cape, very low instability, capped environment here. Just not an environment that is conducive for significant tornadoes, even though we're getting significant tornado matches here. So something to keep in mind. It is a cool feature, though, to kind of tell you what environments may have been somewhat similar to the environment that you're looking at in a given sounding. So now let's take a look at this final box here at the bottom right. This shows us the plot for different types of tornado events. The effective layer STP or STPE with SIN factored in, convective inhibition factored in. So this is based on research from Thompson et al. 2012. And it lists the different tornado types, tornadic supercell types, so non-tornadic, EF0, EF1, EF2, EF3, and EF4 plus tornadoes. And it plots, it took into account a bunch of different cases, the significant tornado parameter, effective layer, significant tornado parameter for a bunch of different cases of all these different types of tornadic events. And it plotted it in these box and whisker plots on this graph. So if you're not familiar with box and whisker plots, we'll take a look at this box right here. So this whisker is going to be our bottom 10th percentile. So the bottom 10% of STP values for all these cases for EF4 plus. Then this is going to be our top 10%, so above the 90th percentile. And this is going to be our basically our sweet spot. This box is going to be our sweet spot for where most of the values happened. Most of the STP effective values were for EF4 plus tornadoes are going to be in this box here. We call this the interquartile range. And then this line here is the median value of STP for EF4 plus cases. So this red line plots the STP, the effective layer STP. You can see that is listed over here in this bottom left box. That is plotted on this graph. And that way it gives us a way to kind of estimate the possible outcomes for a given significant tornado parameter effective layer environment. So if we have a significant tornado parameter of 5, you can see that that line is plotted here. You can see we're almost to the median of that EF4 plus box. We're well above the kind of sweet spot for that EF3 and EF2 and so on boxes. We're entirely above the EF1 and EF0 and non-tornadic boxes. So you can kind of get, in this particular case, that we may see some strong tornadoes with this given sounding and given effective layer significant tornado parameter. Now again, as we've talked about before, the significant tornado parameter is a composite parameter. It's a multiplication of a bunch of different factors: shear, instability, convective inhibition, etc. So it's not a super reliable value when we're making a forecast. Again, we can figure out the chance that an environment will produce significant tornadoes by looking at the overall environment itself. You can see here large instability, very large looping hodographs in the low levels, definitely a deep moist layer here. So you can already see, just from looking at the Skew-T and the hodograph, that we have a chance for any supercell in this environment to produce tornadoes, perhaps some significant. But this gives us a nice way to quantify that using significant tornado parameter, effective layer, for different historical cases that were non-tornadic EF0, EF1, EF2, EF3, and EF4 plus producers. So I don't look at this a whole lot when I'm making a forecast, but it is a nice way to quantify and kind of give you a visual of the possible tornadic outcomes, at least from a given environment, in kind of a rough sense. And this inset here gives us the relative frequency, the probability of EF2 plus tornadoes with any supercell in this environment. You can see that the climatology, sounding climatology, indicates that a value above 0.15 indicates significant tornadoes are possible. You can see here in this environment, we've just based on mixed layer CAPE, we have a probability of 0.13. So basically, that is telling us that based on all historical cases, looking at just mixed layer CAPE, that the probability of a significant tornado is going to be 0.13, 13%. Now, you can see how, I don't want to say useless it is, but how misleading that might be. Because if we're just looking at CAPE, then this model sounding that we looked at should produce a significant tornado. We're seeing almost 3,500 joules per kilogram of mixed layer CAPE here. But if we take a look at shear and CAPE, we'll see that significant tornadoes are pretty much going to be non-existent in this environment, given the lack of low-level shear. So these are just based on individual factors within that significant tornado parameter calculation. ML CAPE, mixed layer LCL height, effective storm relative helicity, effective bulk wind difference alone. So you can see here, for example, just based on effective SRH, just based on the fact the effective inflow layer storm relative helicity is 401 meters squared per second squared, we have a probability of EF2 plus tornadoes at 0.27, basically 27%. And these bottom two here are based on the fixed layer STP and then our effective layer STP down here at the bottom. So if you're going to use any one from this box, it would be the effective layer STP, because that takes into account all of these factors from an effective rather than a fixed layer sense. You can see here that probability using the effective STP of a EF2 plus tornado is 0.32, so quite high. You can see that the color changes based on how high that number gets. So again, it's just a probability. It's just a way to kind of visualize the possible tornadic outcomes of a given environment just using effective layer storm significant tornado parameter and its different terms within that calculation. So not super useful when you're making a forecast. Again, you can gather how likely significant tornadoes are from a given environment, looking at the Skew-T, looking at the hodograph, and the other parameters over here. But it gives us a nice way to give kind of a slight probability, give us kind of a way to quantify that probability of having significant tornadoes with a given environment. So that is going to do it for our deep dive into taking a look at every single nook and cranny of this SPC and model sounding output. Again, we've taken a look at every single parameter here. Not all of these parameters are useful when making a severe weather forecast. They each have their own importance, but again, I don't use a lot of these when making a forecast. I like to look at the overall distribution of moisture, instability, temperature, wind shear in the overall environment rather than just a bunch of different numbers, different individual parameters. But looking at all of these on the whole can be useful, some more than others. But that's going to do it for this look at SPC and model sounding. So that's going to do it for the main portion of this series. We're going to do one more video kind of applying everything we've talked about in this series, and our next video in the series will wrap things up, and we'll be done with this Skew-T and hodograph exploration that we've done. So with that, thanks for watching, and we will see you in the next video.